let's discuss surface integrals. Just generally speaking, in terms of notation, we're talking about how to set up the double integral over surface S of a function f ds. And there's actually several varieties. So we've seen in the flowchart, if f is provided, they just give you a function to integrate, then use it. Not so much to think about there. For the area of the surface S, use f is just equal to 1. For the mass of S, use f is equal to rho, the density function. And what we saw last time, this was new last time, was for the flux of a given vector field, f arrow, across a surface S that has to be oriented or orientable, either language, then we have to use, for the lowercase f that we're integrating, we've got to use capital F arrow dotted with n arrow. And this n arrow, this n is an orientation of the surface S. And for the actual, let's just write out what the flux was here, since this was new as of last time. So double integral over the surface vector field dot d and then s that's either bold or with an arrow on it. However, we're going to make this conversion that d s with an arrow on it is actually n times d s without an arrow on it. So we'll have double integral over the surface of f dot. Now here's the new part. Yeah, so this here is getting replaced with this right there. And so we'll have f dot, now n ds without an arrow on it. Okay, so then the clarification here is that right there, you know, f is, well, f dot n. So that was last time. Now today, we look at sort of a fifth and final type of function to integrate, which will itself have its own physical meaning. Again, there was just a function given, using 1 to get the area of the surface, using the density to get the mass, integrating f dot n in order to get the flux, and now today something new. So we're going to get a new lowercase f to take this spot right there, this spot right over here. And how's that going to work? So a new f, just to preview what's going on, we're still going to be given a vector field, capital F, arrow, and an orientable surface. So I think the key thing to note right now is that given a vector field, capital F, arrow, and an orientable surface S, there's two things that can be done. It's either the flux or the new thing that we're about to try right now. So first of all, I'd like to recall the vector form of Green's theorem. So this was to try to make Green's theorem easier to remember. And it looked like this. If f was the vector field with components capital P and capital Q, and C is the boundary of a two-dimensional region D, then the line integral over the closed curve C of vector field f dot dr arrow ended up equaling the double integral over the two-dimensional region D of the curl of your vector field f, then dotted with, let's fix how that's written, curl of f dotted with the unit vector k dA. Maybe I'll just comment that this maybe looks a little less familiar, but this is really just the line integral over the closed curve C of p dx plus q dy. Maybe that's a more recognizable form of what Green's theorem has looked like. So anyway, there's this equation right here, which is the one way of stating Green's theorem. And now, what we're going to take a look at, now we'll look at a theorem called Stokes Theorem. Okay, are you Stokes? Here we go. Stokes Theorem is morally like Green's theorem. It's just there's a little more complication to it, but it's the basic idea comes from the Green's theorem that's been boxed in red for us. So what's it state? Well, we've got this, so let capital S be an oriented surface bounded by a closed curve, capital C, and this will be denoted C is equal to the boundary of S. Look at how similar that is to C is equal to the boundary of D. Now, C should have what's called positive orientation. We'll clarify what this means in just a moment. Let's just go with this now so that we can first create the connection to Green's theorem. So the thing that we tend to prefer, by the way, for this is that we prefer, I think it's a little more preferable to use language like this. The orientation of C is or must be compatible with the orientation, the n vector function for the surface S. So a lot of things that we're taking a look at have orientations to them or directions attached to them. This way to that way or that way to this way. Okay, so we'll go through that. Don't worry. Let's just finish stating the theorem first. Then the integral over C of f dot dr is equal to the double integral over S of the curl of f dot vector n ds. So that's the way we'll state Stokes' theorem. I would just like to mention, well, let's first of all, let's do the following. Let's point out how similar it is to the theorem that was the vector form of Green's theorem. So this side and this look really just the same. We have a double integral over D, and now we have a double integral over S. We have the curl of the vector field. We have the curl of the vector field. It is dotted with something. Previously, it was a unit vector that was just the constant vector 0, 0, 1, or called K. Now, it's with a unit vector that gives the orientation of your surface. This plays the same role. In fact, this case, you'll see later on, is actually just a special case. And then the ds is a dA. So look at, I mean, the point is this new theorem called Stokes' theorem is very, very similar to the vector version of Green's theorem. One other comment to make is that the way that the book says this, I don't prefer as much, but I think I should just mention that the book's version of the right side looks like this: double integral over S of curl of f dot ds. Now, if all you do is you replace the ds that appears right here with what we have up there, it works out all the same anyway, but I just think somehow this version is a little more memorable because it looks more like this, and to be fair, this version right here is much closer to how the implementation of this eventually goes anyway. So this is the fifth and final sort of new type of integral we do for surfaces. All right, so to finish the list above, so I'm talking about this list over here, 1, 2, 3, 4. We had only just previewed what's the actual text that should belong here. Now it should be really, it should say, you know, the following. It says, when using Stokes' theorem, when using Stokes is a fifth type of integral we do over surfaces, then the lowercase f, you'll see from right here, let me circle this in a new color. You'll see from right here that the lowercase f is going to be curl of the vector field, capital F, dotted with the n vector.